All right. Hello, everyone. My name is Tathagat Das. Everyone calls me TD for obvious reasons. And I'm here to talk about Spark Streaming, how to run Spark Streaming in production. And first of all, a little bit more introduction about me. Okay, good, the clicker works. So who am I? I am in the project management committee of Apache Spark. And specifically, I'm the lead developer of Spark Streaming. I actually started building Spark Streaming as part of my grad school in AmpLab UC Berkeley. And currently, I'm on a sabbatical as a software developer in Databricks. For people, whoops, what did I press? Sorry, I think I goofed up. Thank you. All right, so for people who are not familiar with Databricks, Databricks is the company that started by the creators of Spark. It offers a hosted service on EC2, which Spark on EC2 with notebooks and visualizations all hooked in together in a perfect work environment for data scientists and data engineers. And it provides automated cluster management, jobs, scheduling, jobs, etc., everything all in one place. So anything that you want to do with Spark, you can do it on Databricks, and Databricks is the best place to do anything related to Spark. Okay, quick show of hands. How many people are familiar with Spark Streaming? Oh, wow, okay, that's quite a lot, okay. I had some introductory slides, I guess I'll breeze past them faster than I thought. Okay, cool, that's good to know, that's good to know. So for those who are not familiar, to bring everyone on the same page, Spark Streaming is a scalable fault-tolerant stream processing system. It can take data from lots of streaming sources like Kafka, Flume, Kinesis, plain old Hadoop file system and S3, as well as sockets, Twitter, etc. Process all the data in real time or near real time and push them out into file systems, databases, dashboards, etc. And what sets it apart from other systems is, one, it provides high-level API, which includes joins, windows, all comes out of the box with Spark Streaming, and it translates to 5 to 10 times less code that you would have to write with many other competing stream processing systems. Second thing would be it is fault tolerant, so you get exactly one semantics even for stateful operations. That is a feature that a lot of open source stream processing systems do not have. And third, and probably the biggest difference, is that it is integrated in this part of the Spark ecosystem, which has machine learning algorithms, graph processing algorithms, data frames, SQL, all as part of the ecosystem, which makes it a very unique player in the whole real-time stream processing ecosystem. So, what can you use it for? You could use it for real-time fraud detection. Let's say you're a bank, you want to detect fraud in bank transactions. You can, that's a lot of big volumes of data coming in real time. You can use Spark Streaming to detect frauds like that. You can, if you're running a sensor network, and you're monitoring them, you can react to anomalies you find in the sensor data in real time. Or if you just couch surfing hacker, you could always write your own Twitter app to find cat videos using Spark Streaming. That's big data too, sure. So, digging a little bit deeper, how does it work? The way it works is that Spark Streaming has this thing called receivers. Receivers take the data streams from outside and chops them up into small batches of the order of a few seconds, and then hands it off to the Spark core engine to process them. So Spark processes the batches, and then the final processed data results is pushed out to external data stores also in batches. That's a very basic, simple idea of how Spark Streaming works. To take a look at how a simple word count using Kafka looks like in Spark Streaming, this is how you would write word count in Kafka. This is actual code in Scala language. The first thing you would do is create this thing called streaming context. Streaming context is the entry point for all Spark Streaming functionality. And you have to specify the batch size as part of the streaming context. Now you can use this context to now create this thing called D streams. For in case of Kafka, you can use Kafka utils. It's part of Spark Streaming as it is bundled with Spark Streaming. You can use create stream to create D stream, which is the core abstraction of Spark Streaming. And D stream is essentially represents a data stream. Second, once you have created this data stream, you can now apply these things called transformations, like in this case, flat map. As you can see, what it does, it takes every line in the Kafka data stream, again splits it into words, creating a new data stream, a new D stream called words. And so, and you keep applying these more of these transformations to count the words, and then finally, when you have the stream that has the final result that you want to actually use, you can do something like something simple like print to print a sample of those data on the screen to see what is being generated after all these transformations. But interestingly, all these lines that you have seen till now doesn't actually run anything. It only sets up the computation that needs to be run when data actually comes in. To actually start the whole computation, you need to do this. Ask the context to start. And then the context will actually start the receivers that I talked about. They will start receiving data, and all these transformations will start happening underneath. That's the basic idea behind how a word count in Kafka looks like. As you can see, hardly 5-6 lines of code. And I showed you an example in Scala, but you can write the same stuff in Java and Python. Java being a little bit more verbose because you don't have this nice way of writing functions, nice way of writing inline functions. But you're not just limited to these 3 languages that we natively support. If you have some complex business logic that you have written in some other language like Ruby, you can always use this thing called pipe functionality is in Spark to shell out the data to outside or shell program outside in whatever language and process the data in real time using any other language. So all languages are effectively supported in this way. And who is using Spark Streaming? There's like the list of companies using Spark Streaming is growing very rapidly. I actually cannot keep track of it anymore, but these are like probably 3-month-old set of icons. Some of them, some good players, interesting players would be Intel, Netflix. They have been running Spark Streaming for months for their own users as well as for other companies as well. Intel China builds these pipelines for other companies. So they have been doing production Spark Streaming for a long time. Cisco has been using it. Pearson has been using it for almost 6 months now. So Pinterest, there's a Pinterest blog post about that they are also playing with Spark Streaming and MemSQL. So a lot of people there's actually a very rapidly progressing industry adoption about Spark Streaming. And why they're using it? Of all the possible reasons, the most important reason is the ecosystem. The fact that you can very easily combine batch processing with stream processing. Like for example, you can join a data stream with a static data set. You load the static data set from a HDFS file into this thing called RDD, which is Spark's abstraction of a data set. And then you can join the data stream, a D stream, with an RDD very easily. And which allows you to do a lot of interesting stuff that is pretty hard to do in any other stream processing systems that are not built to interact with this interact in this kind of an ecosystem. You can also combine machine learning with Spark Streaming. You can do learn a model on a large data set. Let's say k-means, for example, learn the k-means model on a large data set and then very easily apply the model to do predictions in again an online stream. You can also do online continuous learning and prediction, and there in Spark 1.2, 1.3 we have added a bunch of algorithms that like streaming k-means, streaming logistic regression, streaming linear regression, which does online model learning and prediction at the same time. Finally, you can combine streaming with SQL. Like for example, you can interactively query the data that is coming in through streaming using SQL. So you can convert not just SQL but data frames. Spark 1.3 came with introduced data frames, so you can take the data generated from streaming, convert it to a data frame, convert it to a table, and then very easily interactively query that table on what is the data that is coming in on the stream. So you can do two kinds of real-time analytics on the streaming data sets. So this was the introduction. From this point on, the curve, learning curve is going to steeply rise up because this was supposed to be an advanced topic, and good to know that a lot of people are familiar already with Spark Streaming. So now I'm going to dig a little deeper and talk about how to run Spark Streaming applications in production. So let's say you have already written the Kafka word count. It runs on your local laptop. Maybe you also run it on a small Spark cluster somewhere. This is the whole program, by the way. What next? How do you actually run it in production with large volumes of data and make sure it is fault tolerant stuff? So the three things you need to consider while you're productionalizing it. One is fault tolerance and the semantics of your application related to fault tolerance, the performance and stability of your application, and for once it's deployed, it is continuous monitoring and upgrading in the case of there is code changes and stuff. So let's walk through, to understand these three, I have to dig deeper and show you what Spark Streaming does underneath. And so this is the deeper view of Spark Streaming. Hopefully I can walk you through and to give you a better understanding of what Spark Streaming is underneath the simple API. So Spark Streaming is just like any other Spark application, since it runs on top of Spark. So the way any Spark application works, and for a lot of you this may be a refresher, is that your user code that you write in Spark runs as part of the driver process. The driver process, given a cluster managed by Yarn, Mesos, or Spark's own standalone cluster manager, the driver asks resources from that cluster and spawns a bunch of executors. Okay. Spawns a bunch of executors. These executors are meant to run the tasks that needs to process the data, and so then driver uses these executors. It launches tasks on them to process the data, and the processed data is finally written to some file system or database. This is again Spark. Spark Streaming is not very different. It is the same. It just has a few more additional moving parts. So given the word count that you have written, you can, it runs in the driver. As part of when you start the streaming context, what the driver would do is actually run a receiver as a long-running task in one of the executors. There may be multiple receivers, so there will be multiple receivers launched on the executors. And this receiver will start receiving the data stream from whatever the source is, Kafka, Flume, Kinesis, whatever, and start dividing the data into blocks and store them in the memory of the executor. What it will also do is that replicate those blocks of data into another executor for fault tolerance. I'll discuss that shortly. But it will do an in-memory replication across multiple executors. And then what the driver in parallel will do that every batch interval, like every 1 second, 2 seconds, whatever you have configured, the driver will launch tasks to process those blocks of data. And after processing those data, it will push the processed results out to whatever external data store you have configured it to use. That's how Spark Streaming works underneath. With this knowledge, let's understand how fault tolerance and the corresponding semantics work with Spark Streaming. So, failures. Why do we actually care about failures? Because many streaming applications have the requirement that no data must be lost. So, they need to provide zero data loss guarantees. Because, for example, you're doing banking transactions, you don't want any of the fraudulent transactions to be lost and not processed. So, depending on that, there are essentially two kinds of guarantees that different applications often want. One is at least once guarantee, that every record in the stream be processed at least once, and exactly once guarantee, as it's obvious from the name, every record must be processed exactly once, no more, no less. So now there can be different kinds of failures in the system. Two critical ones being essentially captures the whole domain of failures is executor and driver. These are two components that are things, so these are two components that can fail. And depending on the requirements of your system, whether it's at least one or exactly once, and the kind of guarantees failures, you need to configure the system and set up the system in slightly different ways. And that's what I'm going to walk you through in the next few slides. So let's understand what happens when an executor fails. So let's say there was this executor with running a receiver, and this executor happens to fail. Obviously, the receiver running on the executor is gone. All the in-memory data blocks in that executor is also gone. But that's okay, because the driver will immediately detect the failure, and the tasks that were running on that executor will be relaunched again on a different executor using the block replicas that is present on other executors. And that's why we actually replicate the blocks, so that this executor failover can be handled. And also for the receiver, which is also another task, will be relaunched again on another executor. So, and this happens on its own, as in you don't need to configure Spark to do anything special. This happens automatically. The trickier thing is what happens if the driver fails. So if the driver fails, all the executors are lost. So all the computation that was going on is lost, all the receivers are dead, all the in-memory blocks are gone. What do we do? How do we recover? For that, what Spark streaming provides is this mechanism called checkpointing. And where the idea is that you take the state of the computation and save it periodically to a fault-tolerant storage. So while the driver is actively running, all the necessary information is saved to a file, let's say in HDFS. So, and using this checkpoint information, what can be done is that you take if the driver fails, you can restart the driver using the checkpoint information. The restarted driver will start new executors, and on the new executors, the receivers will be launched again, and it can continue processing from where it left off. So this is the advantage of the checkpointing. Now, how do you configure this sort of driver restart with checkpointing? You need to do three things. One is obviously configure that the driver process be automatically restarted, and all cluster managers support this, so that part is reasonably easy. Set a checkpoint directory in HDFS compatible file system, so that all the checkpoint information gets saved into that checkpoint directory, and it's also very easy on the context. You can just say checkpoint with the HDFS directory. And the slightly trickier part is that you need to slightly restructure the simple code that I showed you, so that the code can understand the semantics that if you restart the process, I'm going to it needs to read from the checkpoint information. And let me come to that later. Let me first just walk through a little bit on how do you configure the driver restart. So for Spark standalone clusters, you need to submit the job in cluster mode, and then there's this flag called -supervise, which tells the cluster mode that run the driver within the cluster and monitor it, so that if it fails with a non-zero exit code, it will restart the driver process in some other node in the cluster. So that is taken care by the Spark standalone cluster automatically. The details are in the online guide. For Yarn, it is automatically supported. You need to take a look at the configuration to make sure that which states the number of times it will try restarting the application manager, as they call the driver. And for Mesos, Marathon is often used to submit Mesos applications, and that has a capability of monitoring and restarting as well. So all cluster managers actually support this. Now comes the tricky part where you restructure the code for checkpointing. So you need to, so your application can be broadly divided into these two parts. One part where you create and set up the streaming context. Second, where you actually start the streaming context, to start all the processing. So now what you need to do is take all the creation and setup code and put it in a function. A separate function, it's kind of like a factory function if you use. And inside that function, you also need to obviously configure the checkpoint directory. Now, once you have put this into a function, to use this function, what you have to do is take the context.start and rather use this thing called streaming context get or create. And what it does is that it either and what it does is it has this very nice semantics that if in the HDFS directory, it has the checkpoint, it finds the checkpoint information, it will recover the context from the checkpoint information and continue processing where it had left off. Else, if it does not find the checkpoint information, it will call the factory function to actually set up a new context and start from there. And so once you write your code using this pattern, if the code gets restarted, the code will automatically on its own take care of whether it has to start it or restart from a checkpoint information. So this is the restructuring you need to do. Now with all but what it does not handle is that, and maybe some of you have already observed that, is that when the driver is restarted, the new executors are spawned, the received blocks that were in memory before failure are gone. So the data that were received and buffered in memory but not yet processed are all gone. We don't want that. We want to recover that data as well. So to do that, we have this second mechanism called write-ahead logs. And what the idea is pretty simple. It's called write-ahead logs, journals, and the idea is very simple, that all the data that the receiver is receiving is synchronously saved to a fault-tolerant storage as well. So that when the driver is restarted, it can read back those same block information back and continue processing without losing any data. That's the idea behind write-ahead logs. And to recover data from write-ahead logs, you need to do, again, three things. Well, kind of two extra things. First of all, you need to enable checkpointing because you need to set the checkpoint directory, that is where the logs are written. You need to enable the wall explicitly in the Spark configuration. Again, the online web page, the online guide has all this information. And also the receiver that you write, you can actually write custom receivers, but all the inbuilt receivers are also made to be reliable. But by reliable, what I mean is that the receiver must acknowledge the source that the data has been received only after the data has been synchronously written to the write-ahead log. This allows that if the receiver has received some data but not yet written to the write-ahead log, after the driver restarts and the receiver is launched again, that piece of data will be replayed by the data source because the data source has not been acknowledged that that data has been received. So the data source will take care of resending the data. Well, this works for only data sources that can do replay, like Kafka Flume Kinesis. But assuming that, that's what reliable receivers ensure. So with these configurations put into the picture, let's understand the semantics. To understand the semantics, you need to take a broader look at the whole streaming pipeline and understand what each stage does. Because ensuring zero data loss means that every stage in the pipeline needs to give at least one's guarantee, that all the records being processed at least once. And there are essentially three stages: receiving, transforming, and outputting to external data stores. So the transforming part, because of it is Spark underneath, which gives exactly one's guarantees on all the RD transformations, as long as received data is there, all the transformations will be exactly once. Now to ensure that the received data is there, you obviously need to enable write-ahead log and reliable receivers, which gives at least one's guarantees. There is some chance of duplicates between if the data is saved to the write-ahead log, but the system fails before the data source is acknowledged, the data source can replay the data unnecessarily. So there is some chance of duplicate. So it gives at least one's guarantee. Whereas The last part, depending on your data store and the kind of operations that you do, if you do idempotent or transactional operations to push the data out, you get exactly one's guarantee. Overall, this gives in the whole pipeline at least one's guarantee. But again, as I've observed that some applications require even more guarantees. For that, we have added, and this came with Spark 1.3, this thing called exactly once, this thing called Kafka Direct approach, which does not use receivers at all. It in fact doesn't use receivers, doesn't use rightahead log. It treats Kafka itself as a log and reads Kafka like a file system. It manages the offsets on its own. It uses the low-level Kafka API. And so there is no need to configure multiple receivers. There is no need to configure write-ahead logs. It just takes care of it on its own. And you can read more about it if the slides get published. You can read more about it in the links associated with in each slide. But that gives exactly one's guarantees in all the stages, giving overall exactly one's guarantee. A cool thing that you can read about is Netflix did this crazy experiment with this tool called Chaos Monkey that they have, which randomly kills node in a production cluster to see how the cluster or the cluster application actually is fault tolerant or not. So they actually tested Spark streaming with Chaos Monkey, and they found a lot of interesting details like this they had done 6 months ago, and they had found corner cases bugs which we solved, and so they have actually written a blog post telling that Spark streaming can handle all these kinds of failures perfectly, etc. So it's a very interesting read. You should go look it up. You can just Google for it. So that's it about fault tolerance. Let's jump into performance and stability. So to ensure there is a high throughput pipeline, you need to ensure that there is sufficient parallelism in all the 3 stages that I talked about. So let's walk through each of the stages to see how you can ensure that. So in the receiving part, first of all, your data sources needs to be configured so that parallel streams can be read in parallel. In the case of Kafka, you have to set the large number of partitions. In Kinesis, you have large number of shards, etc. Now, once you have those configured in the data sources, in the Spark streaming app, you can create multiple receivers by creating multiple input D streams. And it's actually pretty easy to do. So as you can see in the code snippet, you can create multiple Kafka streams and then union them together to give the impression that as if they're a single stream. But underneath, for each of the Kafka stream, there will be a separate receiver created. So in this way, you can create multiple receivers and which can receive data from multiple partitions in parallel. So this increases the aggregate throughput that your Spark streaming app can consume from Kafka or Kinesis or Flume. Now, to run all these receivers, you have to ensure that there are sufficient number of executors in the cluster itself. This is because each receiver is running as a long-running task. So if there are not enough executors or cores in the cluster, it cannot run. And the good rule of thumb is that if you have to run 5 receivers, you need at least 5 executors in your Spark application. And this is so that there is no more than 1 receiver running in each executor so that they don't have to share the network bandwidth. So that ensures maximum throughput across the cluster. And one corner case is the Kafka Direct approach. Since it does not use any of the receivers, this does not matter for the Kafka Direct because the Kafka Direct, it can parallelize on its own. It doesn't need any extra effort to parallelize it by launching multiple receivers. It will figure out the number of Kafka partitions on its own and make sure it reads from all the Kafka partitions in parallel. Again, you have to have sufficient number of executors to read from that many partitions in parallel. So that's for the receiver. Now, when you want to transform the data, this is where it gets actually quite tricky. you need to ensure that the full pipeline is stable, and by stable I mean that it can process the data as fast as it is receiving. Because if you don't process it as fast as receiving, the data will keep getting buffered up in memory, and eventually your cluster will tip over. You don't want that to happen. And the good rule of thumb to ensure that is that your average time to process each batch should be less than the batch interval. So for example, if your batch interval is 1 second, your average batch processing time should be less than a second, typically good to have around 600, 700 milliseconds with some slack. And this ensures that the previous batch is done processing with processing by the time the next batch is received. And otherwise, stuff will keep getting buffered in memory, and things will fall over. Now, to reduce the batch processing time so that it is less than the batch interval, one thing is add more receivers, because the nodes that are running the receivers are also doing the processing. So adding more receivers and more executors, meaning you're parallelizing the work further. If that is not sufficient, you can explicitly repartition the data as well into more number of partitions across the cluster. Again, parallelize it further. If you're doing some kind of shuffle like reduce and stuff, you should specify sufficient number of reducers, sufficient number of partitions in it, and obviously get a larger cluster so that all these things can be done in parallel. Finally, lower level optimizations like using cryo-serialization can be enabled to reduce serialization costs. If that doesn't work, finally you should try with larger batch durations. If you larger batch duration amortizes the cost of shuffle further, so there's a greater chance that things will be more stable. And if finally you also need to guard against data surges, so that suddenly there is sudden high data rate and the cluster doesn't tip over. You need to limit the ingestion rate, and there are configurations that you can figure out that is there in the streaming programming guide online. The last part is output operations. How do you push data to data stores efficiently? And the important thing to remember is that you should not be opening a new connection to push out a single record. You should actually, rather than doing for each and open a connection every time, you should use for each partition, where you open up a connection, push all the data in a single partition at one go, and then close the connection after that. What's even more efficient is that you don't even open connections at all. You just maintain a connection pool and just get an already open connection from the pool, push the partition out, return the connection back so that other tasks can reduce it. So this is the most efficient way of pushing data out to external data stores. Finally, the last but not the least, obviously you need to monitor your applications, and there are a bunch of ways to do it. In the streaming, in the Spark Web UI, there is this, when you run a streaming job, there's the streaming tab that comes up, and this comes with Spark 1.4. We actually, in 1.4 that is going to be released in next couple of days, we have actually improved the streaming UI a lot. As you can see, it shows statistics over the last 1,000 batches. You can see what the data surges were. Key things to remember here is that you should make sure that the scheduling delay out here stays as close to 0 as possible. It should not be increasing, which means that if it's close to 0, it is stable. And if it's not close to 0, check out the batch processing times for each of the batches, see whether it is more or less than the batch interval. All of that shows up in the UI nicely. Now, if you find a particular batch was actually pretty bad, it took longer than usual, you can now actually start digging deeper into the batch, because you have batch level statistics, like for each batch, what were the data rate, how many records did it process. You can then dig further deep into what were the actual Spark jobs that ran for that batch underneath, and start figuring out what caused the delay and stuff. So all this allows you to do a lot of monitoring of your streaming application. For long-term monitoring, like for over hours and days, what you should do is actually hook it up to something like Ganglia or Graphite. And Spark and Spark Streaming has all these metrics published through this library called CodaHell, which can be configured to either push it out to Ganglia, Graphite, or CSV, XML, and a lot of different formats are supported. And the instructions to actually, how to actually configure Ganglia and these things are actually present on the online guide. Just go take a look, and it's pretty easy to set up. The last part is, now that you have a streaming app running, you may need to upgrade the code to it. How do you actually upgrade your app? So what you should do is shut down your current streaming app gracefully. And by gracefully, I mean that you need to just set this flag when you stop the streaming context. And what it will do is it will first stop receiving all the data, ensure all the received data is processed, and then cleanly shut down. And then once it's shut down, you can redeploy your updated app and start it go over again. And this will ensure that between the upgrade process, you don't lose any data. There are like a lot of different things that I did not cover, especially the memory tuning and GC tuning part, how to use SQL, broadcast and stuff. Refer to the online guide. It has all these details in more detail than these slides. There are details that I actually skipped for brevity, etc. But take a look at the programming guide. It's kind of has all the information over there. Anyway, and before I finish, I'm almost running out of time. If you want to learn more about Spark Streaming, come to the Spark Summit next week. There are many more Spark Streaming talks from different companies like Intel, Netflix, Cloudera, Salesforce, being some of them. They have been running Spark Streaming for a while, and they are giving talks about sharing their experiences. And you learn more about what the problems different companies face and in productionalizing it and how they solved it, nice tips and tricks from them. Also, I'm giving the same talk in Spark Streaming in the Spark Summit as well, the same talk. So if there are some details that were not clear, you can again listen to the talk once again. I'm not sure whether you'd want to, but you can listen to the talk once again, come talk to me at the Spark Summit, and YouTube videos will be posted for the Spark Summit talk, slides will be posted. So don't worry if you didn't get all of the details here. All right, that's my last slide. Thank you. There is a couple of minutes for questions, but I will not hold back people from going to lunch. Maybe I should just walk away.